Okay, we'll get started then. So yesterday we left off with expressions of the form a sine x plus b cosine x. This is in chapter 7, section 2. There's only a couple, this won't take very long, so we'll finish up chapter section 2 and we'll move on. There's only 5 sections in this chapter, so I guess there's a chance we might finish, I guess. We'll see. But our third test will be next week, Tuesday, and it'll cover chapters 5, 6, and 7, just for that to be on your radar. Good. Okay, so expressions of the form a sine x plus b cosine x. This is basically taking advantage of our formula for the sum of two angles, sine formula. Is it somewhere here? Let's look at here. It's working with this. Write it down here. All right, remember our formulas for sine of, say, angle theta plus angle phi. Right, that this guy is equal to, why is this so thick? That sine of alpha plus phi is equal to sine of theta cosine of phi plus cosine of theta sine of phi. And then the other one, that if we have a minus in here, then we'd have a minus in here. It's really the way it works, right? Sine of alpha plus phi equals to sine of sine of theta plus phi equals to sine of theta cosine of phi plus cosine of theta sine of phi. And then if there's a minus, then there's a minus here. Okay, so we want to use this formula. And it kind of fits this form right here, except maybe things get switched around a little bit. So let's rewrite it as, let's put the sign over here. So cosine of phi sine of theta plus, and now sine of phi cosine of theta. All I did is write it in red and switch it around a little bit. So it equals to that. Okay, so if we happen to find an angle phi such that cosine of that angle is a constant that appears in front of sine of theta, plus also it turns out that the sine of that angle equals a constant in front of the cosine, then we can kind of work backwards and rewrite it this way, right? So the example that they're using here is, what if, for example, we are presented, right, with 1/2 sine of x, right? Instead of theta, we're using x here, plus root 3/2 cosine of x. This looks an awful lot like that if we can figure out how to rewrite the half in terms of a cosine of phi, and how to rewrite the sine of phi in terms of root 3/2, then we can kind of go backwards with this process, right? We're given this, we can go backwards with this process and rewrite it like this, sine of the sum of two angles. Good, good. Okay, well, in this initial example, it just so happens that this constant that's out here and this constant that's out here happen to fit one of our standard triangles, right? So if we go to our tried and true standard triangles, right? If we have, this is a 60 degrees, 30 degrees, right? The whole thing stemming from our equilateral triangle where each side was a 2. And we know we have this. And if we think about pi over 3, remember pi over 3 is the same thing as 60 degrees. And pi over 6 is the same thing as 30 degrees. Okay, so if we think about pi over 3, then cosine of pi over 3 is 1/2. Cosine of pi over 3 is 1/2. And sine of pi over 3 is root 3 over 2. Good. So this is a way to replace that. So the 1/2, so we're going to start here. This is what's going to be given. Starting here. There we go. Oh, look, the 1/2. That's the same thing as cosine of pi over 3. That's this guy. And then sine of x plus, and then root 3 over 2. Like, oh, that's sine of phi. That's sine of pi over 3. Good. Times cosine x. And now it fits this pattern. Cosine of an angle, sine of theta, sine plus sine of phi, right? So it fits this exact mold, so I can use this formula to go backwards and rewrite this whole thing. Right? So this is where we're starting. We're given this equals this, and so now we can say that this is the same thing as sine of x plus pi over 3. Right, and that's what they're presenting here. Any questions about this so far? So far, we're good? Okay, so the first types of problems you'll be given in homework are going to be working with these standard angles, right? So you'll see 1/2 and root 3 over 2 and root 2 over 2 a lot. And then variations where we might have a plus or a minus running around. But they're still a little bit limited, right? Because it's not like you can just put any single constant there and any single constant there. It has to be a constant that happens to fit the mold, where we can find an angle such that cosine of that angle equals that constant and sine of that angle equals that constant. So if it wasn't given that way, then what do? Well, that's what we're about to cover. Okay. Questions? Right? So, for instance, if instead, if they very conveniently give you this, you're like, oh, that's great. We started with 1/2 sine x. That's fantastic. But what if we have just some constant 7 sine of x plus root plus 3 cosine of x? Well, now it's not such a clear-cut answer, because we don't have there is no angle such that cosine of that angle equals 7, and there is no angle such that sine of that angle equals 3, right? The outputs of sine and cosine are bounded between -1 and 1. So this one's a little bit trickier, right? Okay, but what we're about to see down here is that we can actually manipulate these, because what we do is think about a triangle that will work, and we're going to end up dividing each of these guys by the perfect value, the perfect number, such that it'll turn them into fractions that will work, such that there will exist an angle such that cosine of that angle equals this fraction and sine of that angle equals this fraction. So what will be that perfect value? That's what we need to figure out. So that's what we're going to look at here. So in general, let's say that they give you some value a sine x, given a sine of x plus b cosine of x, kind of like here. Here's your b, here's your a. Some constant sine of x plus some constant cosine of b. Good. What we want to do, and this is what the formula that we are given. This is going to be the perfect guy, the perfect thing to make it work out. Good. So we're going to take the this guy here, and we're going to multiply it by root a squared plus b squared square rooted divided by a squared plus b squared times all of this, a sine x plus b cosine x. Then we're going to distribute this denominator to both of these, and we'll end up with this guy, right? Once we distribute, we end up with this constant out here that ends up being a squared plus b squared times, and then we have a over square root of a squared plus b squared sine x plus b over square root of a squared plus b squared cosine x. And now this part here will work out just like before. We're going to be looking for some angle, find some angle such that cosine of that angle phi will be equal to this thing, and we'll find some angle such that sine of that same angle phi will be equal to this fraction. Right? That's our goal. Good. So we'd have that cosine of phi equals to a over square root of ax, square root of a squared plus b squared, and sine of phi equals to b over square root of a squared plus b squared. So far we're good? Questions, questions, questions? No? 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 Okay, so let's create a little triangle for phi. Let's arbitrarily put it in quadrant 1. To begin with, and then kind of consider other options later. But okay, so if this is A, this is B, A and B happen to both be positive values in quadrant 1, then it would make sense that the hypotenuse of the triangle would follow the Pythagorean theorem, right? So this length over here is A, and this height over here is B. So this is true, right? A squared plus b squared equals h squared, right, where this is h. So you take the square root of both sides, and it's positive, so we ignore the minus. Good. And here we have something such that cosine of this angle is a over this, and sine of this angle is b over this, right? So it fits this pattern and this pattern. Good. And so in that case, we'd have cosine of phi, sine of phi. Good. Okay, so if we can do that, then we can use our property to recombine this as the sum of x plus phi in the argument of sine. So sine of x plus phi. And there's this constant that exists out here. Okay, so everything we just said can be kind of boiled down into this little box here. If we are given some constant a sine x plus another constant b cosine x, and we want to combine that into a single statement of sine, then it's equal to k sine x plus phi, where k is this constant, it's the square root of a squared plus b squared, and phi is the angle such that cosine of phi equals the constant here, a, over the square root of a squared plus b squared, and the phi is an angle such that sine of phi equals to b over the square root of a squared plus b squared. Good. So the value of this is that we get to convert an addition of two different sine functions, sine and cosine, into a single sine function, and then we see down the road that that's sometimes useful. When we're solving trigonometric equations and we want to solve for x, it's kind of hard to solve for x when x is the argument of two different trig functions. But if we can combine them into one single trig function, it makes it a little easier to solve for x. Good. So far, you're with me? Questions? Anybody have questions? Okay, so here's an example. Let's leave this up here so we can look at it. Express 3 sine x plus 4 cosine x in the form of k sine x plus phi. Okay, all right, so this fits this pattern. This is the of the form A sine x plus B cosine x, right? It fits that mold where the role of A is being played by a 3 and the role of B is being played by a 4. Good. So the first thing we should do is think about that constant k value. So k is going to be equal to a squared plus b squared and square root of that whole thing. So k is going to be equal to 3 squared plus 4 squared and square root of that whole thing. K equals to the square root of 16 plus 9 plus 16, sorry. Nine plus 16. K equals the square root of 25, so K equals to 5. Good. Okay, so we have the K value. Now we need to find this this other thing over here. So we have two things. We have cosine of phi must be equal to the constant A, which was a 3, over 5, the K value. And also we have that sine of phi must be equal to the B, which was 4 out of 5. Okay, well this is one of our standard triangles, but let's see, let's write down. We have this. We have some angle phi, and it turns out that cosine of phi is going to be 3 over 5, and sine of phi is 4 over 5. So this is your standard 3, 4, 5 right triangle. Everyone with me? Good, 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 good. Okay, so this is one of the standard ones we know. Otherwise, we can also, oh man, I should have made more space here. Okay, let me see something. I think they just move on to cosine inverse. Yeah, we just have to use our cosine inverse function. So let's go back over here. Okay, so if you okay, so then we have our cosine of phi is equal to 3/5. So cosine of phi equals to 0.60. Right? We're looking for an angle such that cosine of that angle equals to 0.6, and at the same time, we have that sine of phi must be equal to 4/5. So we have that sine of the phi angle must be equal to 0.80. I hate the zoom button, it just keeps getting activated somehow. Anyway, okay, so if we just use our cosine inverse of cosine of phi equals to cosine inverse of 0.60. This thing. Good. So cosine, God damn, stupid zoom thing. Anyway, cosine inverse of cosine is just going to be phi. So phi equals to cosine inverse of 0.60, right? Which should be the same thing as here. So if we verify it, sine inverse of sine of phi is equal to sine inverse of 0.880. So these operations undo each other, and we end up with phi equals to this. Sine inverse of 0.80. Okay, so if we put it in degrees, let's check it. Calculator. What happened? Okay, so let's go to mode, degrees. We're in degrees, quit, clear. Okay, so we want to confirm what's happening here. So in degrees, this is going to be cosine inverse of 0.60 gets us to 53.13 degrees. And confirming that if we tried the sine inverse, we should get the same result. That second shift sine inverse of 0.8, close, enter, gets you the same thing. Good. And so now we can also confirm in the other direction, so it must be that cosine of 53.13 is really close to the 0.6, true, and also confirm that the sine of 53.13 is again really close to 0.8, with some rounding issues. 53.13 is our answer. So phi equals to 53.13, right? And we get the same answer in both. 53.13. Good. Okay, so now we can kind of put it all together. Starting from the original statement, we have that stop zooming in. Anyway, let's see if we can get this to not zoom in. 3 sine x plus 4 cosine x. So we have that, and then we've decided through our formula that we needed to figure out this value of k. Right? So once we find the value of k, we have this magical property that says that the original is equal to 5 over 5 times 3 sine x plus 4 cosine x. Good. Then we keep that 5 out here, and then we distribute it, and we end up with 3/5 sine x plus 4/5 cosine of x. Good. But then through this great work here, we figure out that this guy is actually 0.6, and it can be written as cosine. This is 0.6, I'll write it again, 0.6 sine of x plus 0.8 cosine of x times 5, right? And then let's bring it up here. And this equals to 5 times, now the 0.6 can be rewritten as cosine of 53.13. Cosine of 53.13 degrees, because this is 0.6 sine of x plus, and then instead of 0.8 can be written as sine of 53.13 degrees. Cosine, so this is sine of come on, Okay. Sine of 53.13 degrees cosine of x okay, right? And that's because this guy was the cosine of 53.13 degrees, and this guy was the sine of 53.13 degrees, right? And that's where this and this came from. Good. And now it fits the exact mold of our formula for the summation of two angles in the argument of a sine function. So now we can rewrite this as this is equal to 5 sine of the summation of these two angles. So it's x plus 53.13 degrees. Good, and that's our answer. Any questions? Stop zooming. Like, I have control zooming here.
Wait, I have something I don't get.
Yes.
What happens to the cosine inside the parentheses?
What happens to the cosine? Oh, I'm taking advantage of this rule. Let's go up here. Remember this rule up here for the sine of the sum of two angles is equal to this complicated thing, right? So I'm going backwards. If I can figure out how to write it as a multiplication of sine theta cosine phi plus cosine theta sine phi, if I can find a way to rewrite it this way, then I can go backwards, right? And that's what we've managed to do here.
Yeah.
Cosine of, right. Okay, so you got it now?
Mm-hmm. Thank you.
Sure. Any other questions from anyone? No. So like I said,
I have a question.
Yeah.
But it's not related necessarily.
It's not related to this?
Not really. I mean, how do we get graded for the support class again?
Okay, I'm not going to answer that question right now. I want to stay on target. That's a very separate question. So maybe during the break or something, you can ask me those things.
Okay.
Or after we kind of finish the class, we can hang out for a little bit longer.
Okay.
Any other related questions on anything with chapter? This is the end of 7.2. I don't know if there's any more examples on here. Maybe there's one more. Let's see what the author did. Same thing. They did the same thing. Found the value of k, found those constants, and then okay. So one more application, and then that'll be the end of section 7.2. Okay, so let's do one more. Very, very similar. Let's zoom in here. Okay, this is going to be the last example in 7.2. Okay, so same sort of deal here. We have negative sine 2x plus root 3 cosine 2x, and we want to rewrite it in the form of k times sine 2x plus phi. Good. Okay, so by our little formula, we know that we have to find the value of k, right? We have a sine of x plus b cosine of x. But in this little example, we have minus 1 sine 2x plus root 3 cosine of 2x. Okay, so the role of A is going to be played by a minus 1. The role of B is going to be played by a root 3. And then because we have 2x instead of x, just think of it as a little unit. Just bring it together as like a little unit, and that's the angle that goes there. Right? I mean, you can also do like a little u substitution if that bothers you. Let's u equal 2x, and then you can proceed to continue to solve this like this, plus root 3 cosine of u. And then it's just a little thing, keep it together. Down the road, when you're trying to simplify your final answer, you might want to deal with the fact that there's a 2 in there, 2x, but for the purposes of combining this into a single sign function, it shouldn't have any effect. Okay? All right, so our little formula tells us that the first thing we have to do is find k. So k equals to a squared plus b squared square rooted. So k equals to -1 squared plus root 3 squared. And then we want the square root. Stop doing that. And then we have, bam, square root of all that. So k equals to the square root of 1 plus 3, and that'll take us to the square root of 4, and that'll take us to 2. Okay, so we have our value of k. So now we know that we have to find phi such that cosine of phi is equal to the a, which was -1, over the k, which is a 2, and then such that sine of phi is equal to the root 3 equals to the root 3 over 2. Is that okay? And this is because this is the a, and this is the k value, and this is the b, and this is the k value. That's how I got those fractions. Okay? So, this turns out to be a standard triangle, right? If we think about our standard triangle where we have our 60 degrees, 30 degrees, we have this guy over here. Okay, so in our standard triangle, this is a 1, this is a 2, this is a root 3. I suspect that it has something to do with 30 degrees, right? I'm sorry, but something to do with 60 degrees, because cosine of 60 degrees, note that cosine of 60 degrees is 1/2, and at the same time, sine of 60 degrees equals to root 3 over 2. So that seems like a possible contender, except that we have to be careful that this is -1/2 and that phi is positive. So in which quadrant is cosine going to be negative, but sine is going to be positive, right? So if you think about it, that's going to be in quadrant 2. So we need an angle such that its reference angle is 60 degrees. We need this, something like this. Right, so we need to figure out angle phi. This is going to be the angle there, such that its reference angle is going to give us 60 degrees, but in quadrant 2. Good. Any questions? And so, of course, phi must be equal to 120 degrees. Good. Questions, 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 questions? Questions, 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 questions? Okay, and so now putting it all together once again, let's get back to this thing. So we had -1 sine of 2x plus root 3 cosine of 2x. Okay, so per the formula, we figured out this k value, that we knew that that was the perfect thing to introduce. So we're going to do 2 over 2 times -1 sine 2x plus root 3 cosine 2x. Okay, so then we distribute that guy, and then we do 2 times -1 over 2 sine of 2x plus root 3 over 2 cosine of 2x, right? Just distributing this denominator 1/2 across these two. And now we said, oh, look, it turns out that cosine of 120 degrees is negative 1/2. And I know that sine of 120 degrees is √3/2. The rest of it stays the same. We have sine 2x plus cosine 2x. And now the whole thing is being multiplied by this constant out here, which is a 2. Good. And now that we've rewritten in this form, now we go, oh, okay, now this happens to be this. It satisfies the form of having 2x plus 120 degrees. Good? Good. We can also factor that and say that this is 2 sine of, and then 2 parentheses x plus 60 degrees. So that's a perfectly good answer there, unless they want it in radians. So then we can turn it over to 2 sine of 2x plus pi/3. Okay, any questions? No? None? We're good? Questions? Let's see if that's what your book did. Okay, so they found the same value of k using the same formula. Author did that. So then they found that phi is equal to 2 pi/3. This is 120 degrees. And so they ended up with the same thing. Good. Questions? This is to graph it. Okay, so a rough sketch of this thing. We know this 2 out here is going to change the amplitude. So instead of the function oscillating between -1 and +1, it's going to oscillate between -2 and +2, right? We know that this 2 is going to make is going to be a horizontal compression. It's going to make it go through its cycle faster, twice as fast. So instead of completing one sine between 0 and 360, it'll complete it between 0 and 180 degrees. Or in radians, it'll complete it in pi. From 0 to pi, it should complete one complete period of sine. Right? That's what this 2 inside the argument here of the sine function being multiplied gives you. And then we know that this plus pi/3 is a shift to the left, right? Counterintuitive to this guy. So it shifts it to the left by pi/3. So you bring those things together and you'll end up with this. Good. Questions? No questions. So 7.1 and 7.2, pretty doable. No problems. All right, I have to do something real quick, so let's take a little 10-minute break and then we'll get started on 7.3. All right, Chapter 7, Section 3, double angle, half angle, and product sum formulas. Okay, so these naturally extend from some of the formulas we already have, and we're not going to spend too much time looking at them. You just have to know them, understand what they're saying, be able to apply them. So we're going to be working with the double angle formulas, the half angle formulas. We're going to evaluate expressions involving inverse trig functions, and then use the product sum formulas. And again, we're not going to spend too much time deriving all of them, but some of them are pretty straightforward. So we have double angle formulas that allow us to find the values of trigonometric functions at 2x from their values of x. So they just help us simplify and expand trig functions and expressions and equations and manipulate them in ways that will help us in the next section, which is trig equations. Okay, so here are the double angle formulas, right? So double angle, remember that this is the argument of the sine function. X is an angle, so we're doubling the angle. If you double the angle, what do you get, right? So for example, if we have if we have sine of 30 degrees, we know that that's going to be equal to 1/2. If we have sine of twice 30 degrees, that's equal to sine of 60 degrees. Oh, come on. I didn't do anything. For all that, I still have the same issues. Anyway, sine of come on. Sine of 60 degrees. Okay, so sine of 30 degrees is 1/2, right? That's one of our standard triangles. Let's put our standard triangle over here. This is 60 degrees. We have 30 degrees. We have 1, 2, root 3. Okay, so if we double the input angle right in here, then, okay, we get the sine of 60 degrees. But notice that we double the angle does not mean that we get to double the output. If it worked like that, then sine of 30 is 1/2, so sine of 60 would be twice that, would be 1. Like, okay, well, obviously that's not true. We know that sine of 60 degrees is root 3 over 2. This thing is just unhappy. So it's not equal to 1, it's equal to root 3 over 2, right? Okay. Well, this little formula over here tells us that what we could do when we want to figure this out is that it's equal to sine of 2 times 30 degrees is like this one, and the formula tells us that it's equal to twice sine of 30 degrees cosine of 30 degrees. Come on. Okay, so this is equal to twice sine of 30 degrees, which is equal to 1/2, cosine of 30 degrees, which is equal to root 3 over 2. Okay, so now the 2 and the 1/2 cancel, and so we see that we get root 3 over 2, just like we had expected, root 3 over 2. Well, I know, maybe if I clear my trash, it might empty some space, and maybe it'll stop bugging me so much. Okay, any questions about that? Good, good, good. Now, where did they get that from? Well, that's actually a really easy formula to derive, because we know that if we have sine of, oh, I think that's a little better. Sine of A plus B is equal to sine of A cosine of B plus cosine of A sine of B. Right? That's the formula for the summation of two angles, sine. We already worked with that one. Good, good, good. Okay, but in our case, what if we had twice x? So then for us, if we have sine of 2x, that's equal to sine of x plus x. So if I apply this formula to this, I end up with sine of x cosine of x plus cosine of x sine of x. Okay. And then the order in multiplication doesn't matter, so I can switch it around and say that this is equal to sine x cosine x plus, and then if I just interchange these two around, write it as sine x cosine x. Oh, well then now they're identical. So this equals twice sine x cosine x. And that's where this formula comes from. Good? Questions, 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 questions? The other ones come in a similar manner. If you think about the formula for adding, so cosine of 2x, think of it as cosine of x plus x. And now look at the formula for the summation of two angles for cosine, and you'll arrive at these variations here. Right? This one is cosine of x. It's cosine of the first angle, cosine of the second angle, minus sine of the first angle, sine of the second angle. Oh, well, it's exactly that formula. Cosine x squared minus sine squared x. That's this one. Good. And now if you just apply our formula for sine squared x plus cosine squared x equals 1, then we can solve for one of the cosine squareds or one of the sine squareds, plug it in, and that's how you get the other two. So, for instance, we can solve for cosine squared. Cosine squared x equals to 1 minus sine squared x. Plug that right in here. So that's 1 minus sine squared x minus sine squared x. And that equals to 1 minus 2 sine squared x. That's how you get this formula. Right? So we got that one, we got that one. And then if instead, at this stage, you solve for x squared, sine x squared, then you'll get to the other form over here. Similar for tangent, you can do sine over cosine, so sine 2x over cosine 2x, and then you can apply these formulas over here and you can get to that guy. Okay? All right, so that's how they come. So that, they shouldn't be too mysterious. They're not that difficult to get. But at the same time, keep in mind that I'm not requiring you to derive any of these blue boxed formulas. Just giving you some idea of where they come from in a kind of not too formal way. Good. But we just get to use them. Use them, apply them, love them, move on with your life. Good, 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 good. Okay, so the types of questions you'll get look like this. Write cosine 3x in terms of cosine of x. Let's get rid of that. Cosine 3x. Okay, so how about if we rewrite it as this? So cosine 3x, we can write it as cosine of 2x plus x. Right? That's 3x equals to 2x plus x. So now treat this as like a little unit thing, 2x. Just treat it like a little unit guy. And then we can use one of our identities to rewrite this any way we want. So how about if we write it as, well, they only want cosine. So how about if we write it as, looking at these guys up here, we have something involving addition. What do I want to do? Yeah, I guess I don't want to do that. In terms of cosine, well, this guy right here is in terms of cosine, 2 cosine squared x minus 1. So let me come back up here. Let me back up here. I don't really want to do that. So let's just apply it in terms of cosine of x. What do I really want to do? I'm having a brain fart here. Cosine 2x. Why do I want to do that? Okay, I'm having a brain fart. Oh, they did want you to do that. Oh, nah, well that's dumb. I don't know why. Okay, yes, they do want you to do that. So cosine 2x plus x. Okay, and so now we have a formula to help us break this down. So we'll end up with cosine 2x and then cosine x minus sine 2x sine x. Right, that's the formula for the addition of two angles. Right, the summation formula for cosine. And now we have a formula we can apply for cosine 2x. In fact, we have 3 of them to choose from. And then we have a formula that we can apply for sine 2x. The sine 2x is an easy one. So sine 2x, that one's just 2 sine x cosine x. So we can replace that right there. We get a minus 2 sine x cosine x is this, and then there's another sine x in here. Okay, and now this gets a little tricky because there's 3 to choose from, and sometimes one works better than the others, so we have to be careful about which one we apply, and there's really no great way to know, just guessing and checking and just kind of seeing what kind of a results we get. But we have the cosine 2x equals to cosine squared x minus sine squared x. And then we have 1 minus 2 sine squared x, and then we have 2 cosine squared x minus 1. So we have to choose. Why does it keep? Any rate, okay. So we have to pick one of those. Try one, see if it leads to something happy, and if it doesn't, then try another one. See, kind of play around with it. Play guess and check with it, and see if you find something interesting out of it. So let's see. If we tried let's just try putting. That one's going to end up with that. That one will end up with that. I don't know, let's just try 1 minus 2 sine squared x, and then we end up with cosine of x. So this would distribute into cosine x minus 2 sine squared x cosine x minus 2 sine x squared, right? Sine x gives you sine x squared. Cosine x. Okay. And then this term and this term are minus 2. They're identical, right? Sine squared x cosine, sine squared x cosine. So this turns into cosine x minus 4 sine squared x cosine x. We can factor out a cosine from both of these and write it as cosine x 1 minus 4 sine squared x. And the instructions were to rewrite it in terms of cosine, but now we can use our identity that sine squared x plus cosine squared x equals 1 and rewrite it as sine squared x equals to 1 minus cosine squared x. Good, so put that right in here, and we're almost done. So we'd end up with cosine of x 1 minus 4 times 1 minus cosine squared x. Which we can simplify just a little bit. Rewrite it as cosine of x 1 minus 4 plus 4 cosine squared x. Or cosine x minus 3 plus 4 cosine squared x. And we can stop there or flip these around and write it as cosine x 4 cosine squared x minus 3. Good. Questions, 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 questions. There's more than one, you'll find in this chapter there's often more than one way to do things, and then there's more than one way, more than one solution potential. So there might be another way of expressing cosine 3x in terms of only cosine of x. And there might be more than one way to do that. If we had gone with one of these other applications instead of using this one, we could have just used this one right over there. And then maybe that would have resulted in something that's a little bit different, but still accomplishes the goal. Questions, 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 questions. See what the author did then. Okay, so cosine 2x. Okay, so we end up with this, and then they use cosine squared x minus 1. So they used a different one than me. And then minus 2 cosine, okay, they did some factoring. And yeah, and at the end of the day, you end up with the same answer I got. Factor out the cosine squared, and you end up with 4 cosine squared x minus 3. So a different path, and then you end up with the same answer. Any questions? No? 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 Okay, double angle formulas. So example 2 shows that cosine 3x can be written as a polynomial of degree 3 in cosine x. The identity cosine 2x equals to 2 cosine squared x minus 1 shows that cosine 2x is a polynomial of degree 2 in cosine x. So what we want to do is we want to take this identity right here, and we want to solve for cosine squared x. Right, so we have this identity of cosine of 2x. We've already established that this is equal to 2 cosine squared x minus 1. Now if we solve for this, we can move this over here. Cosine 2x minus 1 becomes plus 1 divided by 2 equals to cosine squared x. Okay, so we'll use this in a little bit. This is what we call the power reducing formulas. Okay, we'll get back to that. So here we go. We have cosine squared x equals to 1 plus cosine 2x over 2. Right? That's this same one we just solved right here. Cosine squared x is cosine 2x plus 1 over 2. And then we can do a similar thing with the other version of the cosine 2x function. We also know that cosine 2x is also equal to 1 minus 2 sine squared x. That's the other formula for the double angle formula. The other double angle formula for cosine. And then again, if we solve for the sine squared, we end up with cosine 2x minus 1 equals to negative 2 sine squared x. Divide everything by negative 2. Divide everything by negative 2. Stop. I don't know what it is. It's just like hypersensitive, and everything I touch apparently gives me weird menu options. So we get cosine 2x minus 1 divided by negative 2 equals to sine sine 2x. Stop it. It's probably because this is a Microsoft product. any rate. Okay, so then we simplify this, can distribute, move this around, and we end up with positive 1 minus cosine 2x all over positive 2 equals to sine squared x, right? And that's where this formula comes from. Good. Okay, so hopefully it's kind of clear where these formulas come from. They're just derived from our double angle formulas, and our double angle formulas come from the formulas we had before about adding two angles. Right? Okay, so now when we have them, the value of these is that we get to lower the powers. They're the lowering powers formulas, so that we can express something that is squared into something that does not have a square on it. It's just a cosine or a sine of a double angle. Good. So we can express something being squared in terms of the first power of cosine in this case. Express sine squared x cosine squared x in terms of the first power. Okay, well, you could do this in a couple of different ways. My first thought is that this looks an awful lot like sine of 2x equals to 2 sine x cosine x. Come on, computer. Cosine x. This looks an awful lot like that, except it's squared, something to do with a squared. So note that if this was a 4, if I squared this side, 2 sine x cosine x. If I squared the whole thing, I would end up with 4 sine squared x cosine squared x. So that's what this kind of looks like, except it's missing the 4, right? So I'm going to do this. Sine squared x cosine squared x. I'm going to throw in that 4. 4 sine squared x cosine squared x. And now it looks exactly like that, except I can't just go around throwing in a 4, so I'll have to throw in a 1/4 in front of it. Right? But now this part in here looks like 1/4, and this looks like 2 sine x cosine x squared. And this ends up being 1/4 sine of 2x squared. Okay, so this is equal to 1/4, and writing it in a slightly different way, this is just moving this squared into there. This is sine squared of 2x. Okay, so I want to use the power lowering formula for the sine function when the angle is 2x. Good, and then that formula is right in here. It's this guy. It's going to be 1 minus cosine of twice the angle. So this will be equal to 1/4 times 1 minus cosine of twice the angle. And let me put it in color. This angle was 2x, so that's the angle that goes in here, 2x, all over 2. Is that okay? Power lowering formula says that whatever the angle is in there, you're going to double it in there. Good. So then we simplify life a little bit. This is 1/4 times 1/2 minus 1/2 cosine of 4x. And then this becomes 1/8 minus 1/8 cosine of 4x. And that should be our final answer. Any questions? Nope. No questions, no questions, no questions. So this was not the only way to do it. The other thing you could do is just apply this formula twice and simplify as much as you can. So apply the formula for sine squared, apply the formula for cosine squared, distribute, combine, do all the crazy stuff, and then you should get the same answer toward the end. Sine squared x, cosine squared x. So sine squared x, we just established that's equal to 1 minus cosine of twice the angle, so in this case twice x, all over 2, times cosine squared x, well that's just going to be 1 plus cosine of 2x, all over 2. Good, that's what this is. Then, and don't mind that little wiggle there, let's just skip down here. This is going to be equal to 1/4. Let's just pull that out. 1/4. And then this, 1 minus cosine 2x, 1 plus cosine 2x. Good. So we can FOIL all this, but note that this is conjugate pairs. It's a binomial. They're identical in every way, shape, and form, except one has a plus and one has a minus. So this is going to turn into a difference of squares. This is going to be 1/4 times, and it's going to be 1 minus, right, 1 squared minus cosine squared of 2x. Right, 1 times 1 is just going to be 1 squared. 1 times this is this, and then minus 1 times this. So those middle terms will cancel, and then we'll end up with minus cosine squared 2x. Good. So we end up with 1/4, 1 minus, and then we apply our formula for cosine squared one more time. And the formula is 1 plus cosine of twice the angle. So again, the angle here is 2x. So there will be twice 2x. We're going to get to 4x. All over 2. Make sure you put parentheses because this minus applies to the whole thing. And then we try and simplify this. This is a 1/4 parentheses. This is going to be 1 minus 1/2 minus 1/2 cosine of 4x. 1 minus 1/2 is equal to positive 1/2. 1/4 positive 1/2, combining these two, gives you this guy. And then we still have this minus 1/2 cosine of 4x. And when we distribute the 1/4, we get the same answer as this one. Good. So more than one way to get to the same answer. Any questions? No questions, no questions, no questions. No. Okay. Author did the same thing. Okay, they went, here we have the slightly longer version of applying it to the sine squared function, to the cosine squared function. Good. Multiply. Okay, good. Apply it one more time. Yep, same thing I did, and we end up with the same answer. Or then the other way. The other way. So the author did the same thing, they did both. Good, good. Okay, half angle formulas. Again, these are derived from our prior results. So we just established that cosine squared x is equal to 1 plus cosine 2x all over 2, right? Okay, so this one is twice as much as that one, which is the same thing as saying that this one is half as much. Right? Like if this is 15, then this has to be 30, right? It's twice as much as that. Or if this one is 10, then this one is 20, right? It's twice as much as that. Well, you can also look at it from the other direction. If this is 30, then this is half. And if this is 20, then this is half, right? Okay, so instead of writing it as cosine squared x plus cosine twice x over 2, we can equally write it as letting this be x, and though this one will be x over 2. Right? Same thing. Stop it. Good. Okay, and then we just slap in a square root, and that's how you find these formulas. So now, slap in a... Oh, come on. Now we just find the square root of the whole thing. And so cosine of x over 2 is equal to plus or minus the square root of 1 plus cosine of x over 2. So this lets you work with something that that has a fractional, angle times a half. It's another way to look at it. And rewrite it as cosine of a half. So it's something else that gives you a transformation ability. Now, be careful with this plus and minus here. We've covered this before. I mentioned this before. This does not mean that both answers are true. In algebra, when we get a plus or minus, we get two possible answers. But here, it doesn't mean that both answers are true. It means that you have to think about what quadrant you're in. Because depending on the value of this angle here, it might be that cosine is positive or that cosine is negative. Right? So it takes a little bit of thinking, right? Depending on which quadrant the angle here lies in. Okay? All right, so this helps us when we're working with our traditional values, our traditional triangles, right? Remember that a lot of what we do is pretend we don't have any technology and go back to the old school way of doing things, right? And then we have 45 degrees there, and we have 45 degrees there. Good, so this is 1, this is 1, this is root 2. And then we have another standard triangle where this is 60, this is 30, this is 45 degrees. So this is 1, 2, root 3. So a lot of what we do is work with these by hand. And that's what these things are really useful for, to be able to expand our ability to find sine, trig functions. So we know how to find, or we know the values of sine, cosine, and tangent of 45, 30, 60 degrees. But this allows us to expand a little more because, okay, what is sine of 22.5 degrees? It's not one of our standard triangles, so we don't really know how to find it, by hand. We could just plug it into our calculator and get an answer. That's fine. But this is asking us to do it by hand, right? The code words of find the exact value means that don't use your calculator. Right? Keep that in mind for the test. If it says find the exact value, it means don't use your calculator. So sine of 22.5 degrees, when you get this, you have to recognize, you have to note that this happens to be half of one of our standard angles. This is equal to sine of 45 degrees divided by 2. Right? That's what 22.5 degrees is. Good. And according to our formula, this is going to be equal to plus or minus the square root of, and this is going to be 1 minus cosine of 45 degrees divided by 2. Okay, that's just a straightforward application of this formula for sine. Sine of angle over 2 is equal to plus or minus the square root of 1 minus cosine of the angle divided by 2. And the benefit of that is that I know what cosine of 45 degrees is. Good. Now we get this plus or minus, but we have to think about what we expect the answer to be. 22.5 degrees is in quadrant 1, so I expect this to be positive. Right? Positive. This is in Q1. Right? This angle is in Q1. Q1. Good. Good. Okay, so that's how I know that this one is the correct answer, and I can ignore the minus. Good. Okay, cosine of 45 degrees, we know what that is. So this is going to be equal to the square root of 1 minus root 2 over 2 divided by 2. So now it's just a little bit of algebra to simplify this. We need a common denominator up here, so let's multiply this by 2 over 2. Get rid of that one. So we'll end up with 2 minus root 2 divided by 2. The whole thing gets divided by 2, and it's inside this root. So now think of it as a giant fraction, where the numerator is a fraction, the denominator is a fraction. So I'm going to say that this is equal to 2 minus root 2 over 2 times 1/2. Right? It's the numerator times the reciprocal of the denominator, and the whole thing is still inside that root. Good. Now these guys multiply, and we end up with 2 minus root 2 over 4 still inside the root. And so now we can push that out and end up with 2 minus root 2 all over 2. There's a fun answer. And that's what sine of 22.5 degrees is. Any questions? Nice thing here is that we can confirm this, verify it with our, come on. Come on. So we can confirm that this is true. Let's try that. So let's do 2 minus, and then the square root of 2. Square root of 2. And then I want to take the square root of that whole thing. So the square root of the previous answer. That takes care of the numerator. Is that. And then divide that whole thing by 2. And we get that. Okay? Or if you want, you can type in the whole thing all at once. Put a parentheses, and then it's like the square root of 2 minus the square root of 2. And we're going to get out of that, close parentheses, divided by 2. There. So we get the same thing. There's that complicated statement. And then to confirm that it equals to what we expect, that's sine of 22.5 degrees. Bam, we get the exact same answer. Good. Questions, 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 questions? No? 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 We're good? We're good? We're good? Okay, so moving on, let's see. The author did the same thing, I'm sure. Yep, noting that 22.5 is exactly half of 45 degrees. And then we can apply our formula, and we end up with the same answer. So this expands our the number of angles we could work with based on the two simple triangles that we can get. So instead of just working with 45 degrees, 30 degrees, and 60 degrees, and 90 degrees, and maybe 180 degrees, right? We have some very simple standard angles we can work with. And now we can expand that because now we can add those angles together. We can subtract those angles. We can multiply those angles by 2. We can divide those angles by 2. So it's expanding the number of angles that we can work with by hand without the use of a technology device. Of course, that doesn't mean we can answer anything. Right? At some point, we still are going to need calculators to find some values, but it gives us more room to play with and not have to do it with technology, find exact answers of things. Okay, expressions involving trigonometric functions and their inverses arise in calculus. In the next example, we illustrate how to evaluate such expressions. So evaluate the expression sine 2 theta, where cosine of theta equals to negative 2/5, and theta is in quadrant 2. Okay, so given the information that they provided us with this information right here, so we know we're in quadrant 2. Let's draw a triangle in quadrant 2. So there's a unit circle, and this comes over here, and this comes over here. So this is an angle theta, right? And then there's a reference angle over here. And this is a right triangle on the unit circle, right? So it kind of comes this way and goes that way. Should have done the unit circle first. Okay, you get the point. It kind of goes like that. Okay, so cosine is equal to negative 2/5. So that must mean that this little space over here, this must be negative 2. And so therefore that must be 5. Cosine of it equals to adjacent over hypotenuse. So now this missing side over here, y, well, we get to use our Pythagorean theorem for it. Y squared plus negative 2 squared must be equal to 5 squared. Good. So y squared plus 4 equals 25. Y squared equals 21. So y equals to plus or minus root 21. But from the picture, I can tell that it must not be the negative. So we ignore that minus because we're in quadrant 2. Nor in quadrant 2. And that's what the value of y is. Y equals positive root 21. Okay, so from this little picture, I can describe all the other trig functions of phi. So now I can come back over here and work with this thing. Sine of 2 theta. Well, my double angle formula tells me that this is equal to twice sine theta cosine theta. And so this is equal to twice sine of theta, which is equal to root 21 over 5, times cosine of theta, which is negative 2/5. Good. So my answer is going to be negative 4/5 root 21 is equal to sine of 2 theta. Any questions? No questions, no questions, no questions. So draw your angle, make sure you're in the right quadrant, make sure all the signs match up, create a triangle, find all the missing sides if possible, and then now you have a way of finding all the standard trig functions of theta. Good, good, good. Okay, let's see here, same thing, triangles, they did. Found the missing side, root 21, and same answer we got. Good. So this is the author's way of doing it, and they did the same thing I did. No questions, no questions, no questions, no, 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 no. Okay, the sum to product formulas. These are a little crazier to figure out where they come from, a little bit more. A little bit more involved, but not much if you invest a little time into it. So here are the formulas for them. I'm not going to really talk about where they come from for the sake of time. So we just have to use them and understand them. So what this does is it gives us the ability to express a multiplication of a sine and a cosine, or a cosine and a sine, or a sine times a sine. Right? So it gives us a product, a multiplication, into a summation of the two functions. Right? So that might be valuable in some ways. Like I said, a lot of this is even more useful in the next section, where we're doing trig equations and we need to manipulate our results in order to solve it and simplify it. So we can go in either direction. So very often you'll find that we work with something that looks really messy like this one, and we want to go backwards and express it as something like this, which is a much simpler thing to work with. Right? Especially depending on the specific values of u and v. We might know sine of u and sine of v. Maybe that's one of our angles, our standard angles. But then maybe their difference or their summation might not be a standard angle. So it might be useful to use these identities to transform our expression. Good. Good. Okay. So here they talk a little bit about how to get those formulas. And then we have the sum to product formulas. Again, I'm not going to spend much time on where they get these from, and you're not responsible for that either. I'm not going to ask you to prove this or something. You just have to use them, know them, love them, apply them, and move on with our lives here. So, okay, we got verify this identity. Sine of 3x minus sine x, all divided over cosine 3x plus cosine x. Okay, how do we verify this identity? Not easy, right? Identities can be really, really hard. There's no straightforward way of doing it. A common mistake, though, at this point is this, that people think that this is true. Sine 3x minus sine x. Very common mistake is people think that this is something you can factor. Sine 2x minus 1, right? That's not true. This is a 3 multiplying the angle. It's triple the angle. It's not the same thing as cubed, right? So this is commonly mistaken for this one, sine cubed of x minus sine of x. This one you can factor out as sine x. Sine x equals to sine squared x minus 1. So this one is okay. This one is gibberish. This one's good. This one doesn't make any sense. Good, 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 good. Okay. So it can be a little tricky to figure out what to do with these guys. So sine 3x, sine x. So if we look at, say, for example, this one, we have sine of the angle minus sine of another angle is equal to this, where we add them or subtract the angles that are given. So if we add them, we end up with 4 divided by 2. That's going to be twice x. Okay, interesting. And if we subtract them, we end up with 2x divided by 2, which equals to x. So that could be useful. So I'm going to apply this application to the numerator. And let's do that. And I don't know if this is the right way to do it. That's what makes these really hard. There is no really clear way of knowing which property will help you when. You just have to try different things. So just working with the numerator, I get sine 3x minus sine x. And I'm going to say that this is equivalent to twice cosine of, and then what you do is you add the angles. So this would be 3x plus x over 2, and then multiply it by sine of, and then it's going to be 3x minus x over 2. Good. Just a straightforward application of this thing. It's this guy goes there, and this guy goes there and there, right? These two angles get added, that goes there, divided by 2, and then these two angles are subtracted in this order, and then that goes there. Good. Questions, questions, questions? So then if we simplify that a little bit, we end up with 2 cosine of 4x over 2, sine of 2x over 2, and then this simplifies to 2 cosine of 2x sine of x. Okay, we're not there yet, but we're getting closer. Good. And now for this one, let's work with this formula, right? Same thing, very, very similar. We end up with cosine of, add the two angles, divided by 2, times cosine of subtract the two angles, divided by 2. So let's put it right here. So this is going to be cosine of 3x plus cosine of x is equal to twice cosine of 3x plus x divided by 2, cosine of 3x minus x divided by 2, and that'll be 2 cosine of 4x over 2, cosine of 2x divided by 2. So we end up with 2 cosine of 2x cosine of x. Good. So now we're ready to substitute it all into here, and we're ready for our proof. Proof. We start with the left-hand side, which was equal to sine of 3x minus sine of x, all over cosine of 3x plus cosine of x. This is equal to 2 cosine of 2x sine of x, all over, this one was 2 cosine of 2x cosine of x. All of this stuff cancels. Bam, 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 bam. And over here, we end up with sine x over cosine x, which is equal to tangent x, and then you're done. Right? You started with the left-hand side, and you ended up with the right-hand side, and you've done yourself a nice formal proof. Right? Whenever they say verify or prove an identity, you need to put it in this form. Start on one side, and then do work, 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 transforming, canceling, reducing, until eventually you get to the other side. Right? Do not make the mistake of multiplying both sides of the equal sign by the denominator. Right? We're not solving an equation here. You don't want to do that. Good. When these get larger, you're going to have to organize your work. It might be that this question, figuring out how to simplify the numerator, it only took us 1, 2, 3 lines, not too bad. But as they get more complicated, it might be that the numerator takes 8 lines, 10 lines, right? It might be a long, long, complicated thing we need to figure out. And same thing with the denominator. So you might have to organize it into some other section of your answer, right? Maybe this is on page 3 or something, So sometimes I do this kind of thing. Maybe a single star, a double star. And then when you present your formal proof over here, then you could say, for this, C star, and for that, a little asterisk, C double star, and then organize it somewhere in your paper. Right? Eventually, you get to math problems. They're so long that you have like a table of contents for the solution. Right? I remember taking tests where they give you that little blue book, and you kind of skip around, and you have to organize separate little pieces of work that you do somewhere. Skip over to page 8 and solve something. Skip over to page 10 and solve something else. Go back to page 1 and you put your solutions and you combine it into a nice little presentation, and you put, see page 7 for this, see page 10 for this, put a little table of contents to help the reader organize, see where your thoughts were and how you organized and put the whole thing together. So keep that in mind. Make sure that you don't throw this away, though. This is valid work. If you just turn this in, you're not going to get full credit. You need to convince me that you know the answer, right? This isn't about you giving me the answer. It's about you convincing me that you know that that's the answer. If I don't feel convinced, you won't get full credit. Okay? Any questions? Questions. I think that's basically it for this section. Start with the left-hand side, apply the formulas. Yep, the author did the exact same thing I did. All right, cool. Thank you. All right, chapter 7, section 4, basic trigonometric equations. So 7.4 and 7.5 are about the same thing. They're about trigonometric equations. Really, it should have just been one big section, but the author chose to chop it up into the basic ones, the easier ones, and then the more complicated ones. So good news, 7.4 is a little easier. So we're going to look at some basic trigonometric equations, and then we're going to solve trigonometric equations involving factoring. So as the title suggests, these are some of the easier ones. So that's a good way to kind of get started with it. Okay, so here is a couple of examples of some equations, trigonometric equations. So obviously they're kind of like algebraic equations, except they involve trigonometric functions. Note that this first one here is an identity. It means that it's true no matter what the value of theta is. No matter what angle you choose for theta, this statement is always true, right? That's what makes it an identity. Whereas these other ones are sometimes true, sometimes false, depending on the specific value of theta. So solving it would mean that you find all the angles such that it makes it a true statement. There might be an infinite number of angles, there might be no angles, maybe it has no solution. But that's your mission, right? To try and figure out what values of theta make it a true statement. Maybe an infinite number of values, maybe no values at all. Good. Okay, so basic trigonometric equations involve a trigonometric function equal a constant, and then we want to use the inverse trig functions in order to find the angle theta. So here's a simple example, very simple example. Sine of theta equals to 1/2. Right, so in fact, this one we can solve without even technology, since this goes back to one of our standard triangles, right? Go back to our standard triangles, 60 degrees, 30 degrees. Right, this is 1, this is √3, this is 2. Okay, sine of an angle equals to 1/2, so that's got to be 30 degrees. Okay, so we have sine of theta equals 1/2. So I'm going to apply the sine inverse function of sine of theta equals to sine inverse of 1/2. And this would mean that theta equals to sine inverse of 1/2. Now remember, let's go back to our sine function. Go away. Our sine function looks a little like this. One period of it goes up, comes back down, and goes back this way like that. But remember, then it keeps going. Okay, so half is, stop it. Okay, half is somewhere around here. So we're looking for the angle such that sine of that angle equals to 1/2. That'll be this one. And from what we can see right here, that means that this is going to be equal to 30 degrees. Good. 30 degrees is the answer we get from here. But we don't want just one answer, we want all of the answers. And from the graph of sine inverse, from the graph of sine of x, right, this is x, we can see that there is more than one answer. There is the standard one in quadrant 1, but if we keep going, I don't know what just happened. If we keep going, then we have another answer over there. Good, there's going to be some other, some other answer over there. that gives us the same thing. There's some other angle over here. I don't want to put a question mark. How about A? There's some other value over here, A, such that sine of A equals to a half. And if we allowed our sine function to continue, it comes back this way, comes back up that way, comes back up this way, comes back up that way, then we would see that there are, in fact, a couple of other values over here. There's another value over there, there's another value over there. And if we let the sine function continue in this direction, we would see that there's more values over there. So there's an infinite number of angles such that sine of that angle equals to a half. That was really the issue with sine inverse. We can't go backwards and have a specific value in mind. So the way we solve this is to restrict the domain of sine. Remember that the sine function is restricted to go from negative 90 degrees to positive 90 degrees. Right? So the sine inverse function is only defined in this segment right in here. Good. So that's how we got this answer. But we have to be aware of that because we want all of the answers. Good? Good. Questions? So now going back to the unit circle, kind of a combination of knowing the sine function and being aware of where you are on the sine function, and then a combination of knowing the unit circle description of sine and cosine functions. We know that sine is going to be positive in quadrants 1 and quadrant 2. Right? So here is this triangle in quadrant 1. Comes up there, comes down this way. Here is 30 degrees. Right? And we know that this is going to be the result of sine of 30 degrees equals to a half. I know it's not very accurate here, but you get the point. So that's going to be half. And this is going to be the ordered pair cosine of 30 degrees comma sine of 30 degrees on the unit circle, right? Given that this is the unit circle. Good. Okay, so my point is that this sine is positive in quadrant 1, but it's also positive in quadrant 2. So we have to think about this other triangle over here. Comes this way, comes back over here, and it has a reference angle of 30 degrees. So there is another angle that goes from there to there, such that it creates a reference angle of 30 degrees in quadrant 2. Good. And so clearly that's going to be 150 degrees. Great. So from all of this, we can conclude that sine of 30 degrees equals to 1/2. But so does sine of 150 degrees. Oops. So does sine of 150 degrees. They both give you 1/2. Good. So these are two angles that work. So from there, we've confirmed that this value here, right here on my graph, coming this way, that this value, A, is really 150 degrees. That looks messy. But this value is actually 150 degrees. Good. Questions? Once we find the two values in our standard period, one standard period from 0 to 360 degrees, once we find these two values, then we can find the rest by noting that it's the period of sine has 360 degrees. God damn it. Stop it. Because the period is 160, the period of sine is 360 degrees, then the distance from this one to this one will be plus 360 degrees. And from this one to that one over there will be minus 360 degrees. Okay. Likewise, once you find, oh, man, this thing is just killing me here. Likewise, the distance from here to here would be minus 360 degrees, and the distance from here to there would be plus 360 degrees. Good. Okay, so back to this equation. It looks simple enough. Apply the sine inverse to both sides. You get to the 30 degrees. You have to be aware that this value is going to give you an angle trapped between negative 90 and positive 90 degrees, always, right? That's the range of the sine inverse function. It's going to give you something in this black segment of the sine function. And then it's going to be up to you to realize where the other ones are. Okay? And because the period of the sine function is 360 degrees, the other ones are going to be found by multiplying, by adding or subtracting multiples of 360. Right? So theta equals to 30 degrees, or theta equals to 150 degrees in quadrant 2. And then all our solutions are then presented as theta equals to 30 degrees plus 360 degrees k, or theta equals to 150 degrees plus 360 degrees k, and this is where k equals ... negative 3, negative 2, negative 1, 0, 1, 2, 3, ... right? It equals the integers. K equals any integer, including positive or negative, right? So that's why I only put a plus there, because it equals positives, or k can be a positive or a negative. On the other hand, what you could also do is put theta equals to 30 degrees plus or minus 360 degrees k, where k just equals to 0, 1, 2, 3, or just k equals any natural number. The only advantage of doing it this way is that maybe it's like a subtle reminder to people that you can also subtract multiples of 360 degrees. Whereas when you do this, a lot of people forget that the k being allowed to be an integer is allowed to be negative, which means you ultimately subtract. So it just makes it a little easier to remind people to make sure, don't forget that you can also subtract the multiples of 360. Any questions at all? No. And then, of course, you can also present the same thing in radians. All the same work applies. You can think of it in degrees and then come back and rewrite your work in radians. 30 degrees is pi over 6 plus or minus 2 pi k. Good. And then to find 150 degrees, remember that we found it by taking 180 minus 30 to get to 150. So this is equal to pi minus pi over 6, which is going to give you to 5 pi over 6. So the other answer is theta equals to 5 pi over 6 plus or minus 2 pi k. Again, this is where k equals 0, 1, 2, 3, 4, ... Any questions at all? 6. No questions, no questions, no questions. No? All of this made sense? Finding all your other values? Okay, see if the author had better graphs, probably. So here's the work the author did. Quadrant 1 is pi over 6, that's 30 degrees. So we have to find another value in quadrant 2, that's going to be the 150 degrees, that's 5 pi over 6. And the reason we're in quadrant 2 is because sine is positive, gives you a positive value, right? Positive 1/2 in quadrants 1 and 2. So you find your two values and then you multiply, you add multiples of 2 pi. And so here they left it as a plus 2k pi, keeping in mind that k is an integer, so it could be positive or negative. So don't forget that you're allowed to subtract multiples of 2 pi. Any questions, any questions, any questions? Questions. And again, they have a nice picture of it. Here's your sine function. One period of the sine function is this yellow part. We found the two values that work in quadrants 1 and 2, but then there's this infinite number of other possible answers that come as a result of taking this one and adding 2 pi to get to this one. So if I want to go the connection between this one and this one, right? If I take this one and I add 2 pi to this one, I'll get to this one. The x-coordinate of the ordered pairs. Is that okay? So the x-coordinate of this one, so if I want to find the ordered pair of this one, it would be 5 pi over 6 plus 2 pi. That would be the x-coordinate. And of course, the y-coordinate is just a half, right? All of these points are points such that the output equals to a half. Good. Any questions? Questions? No? This guy over here, if I want to find the ordered pair of that one would be equal to the 5 pi over 6 minus 2 pi, right? And then comma 1/2. Any questions? No. Okay, tangent theta equals to 2. Well, this one, I don't think you can avoid using a calculator, right? Because that's not going to be anything that fits into our standard triangles. So let's just apply it. Tangent of theta equals to 2. Let's solve for it. Tangent inverse of tangent of theta equals to tangent inverse of 2. So that's just going to be theta equals to tangent inverse of 2. So we'll just have to use our calculator to find it. But just keep in mind that your calculator only gives you a very limited picture. Right, let's do the sketch of tangent inverse. Let's get rid of that. The sketch of tangent. So tangent will go like this. And remember that there are vertical asymptotes here. That's an asymptote. Here and here. So, vertical asymptotes. And this is at x equals to 90 degrees. And this is at x equals negative 90 degrees. Good. So we're looking for something involving 2. So here, let's say that here is 2. So we're looking for an angle here, theta, such that tangent of theta equals to 2. Right? That's what we're looking for. So when we apply our tangent inverse function to our calculator, we'll get the angle we're looking for. Come on. Okay, so tangent inverse of 2. Tan inverse of 2, close parentheses, enter, 63.43. 63.43. That's what this is. Over here. So that means this is 63.43 degrees. Good. So punching that in our calculator, we get 63.43 degrees. So we're almost there, except we want to find all solutions. We found one solution. We found one value of theta such that tangent of theta equals to 2. But we've got to find the rest, and to do that, we just have to remember that the tangent function has a period of pi. It continues that way, and it continues that way, and the period from the distance from there to there is going to be equal to pi. Back to this. Let's pick a different color. Purple? The distance from there to there is 180 degrees. It's pi, right? So the same thing happens here. Okay, so now there's got to be another value there, right? There's some other angle over here, angle alpha, such that tangent of alpha equals to 2. And there's another value over here, right, phi, such that tangent of phi also equals to 2. Good. And because the period is 180 degrees, what we have to do is add and subtract. Whoa. What we have to do is add and subtract multiples of 180. This guy to that guy is plus 180 degrees. And this guy to this guy is going to be minus 180 degrees, right? The x-coordinate of it. Good. So if I wanted to find the, if I wanted to write down the ordered pairs of this point right here, this point has the ordered pair of 63.43 plus 180 degrees, comma, 2, right? The output is definitely 2. Good. And this point over here is 63.43 minus 180, comma, 2. Good. Good. Okay, so that helps us write down all possible answers. Theta equals to 63.43 degrees plus or minus 180 degrees k, and this is where k equals 0 or 1 or 2 or 3 dot 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 dot, or k equals naturals, any natural numbers. Good. Any questions? Questions? Good. Okay. You can also do it in radians. So we got, if we do it in radians, tangent inverse of 2 is going to get you to 1.12 radians in radian mode. And then we add multiples of pi instead of 180 degrees. So we end up with 1.12 radians plus k pi. And here's a nice picture of our result. Any questions? No questions? Okay, here's a couple of other examples. Final solutions of this equation. Okay, so now we need to do a little bit of work before we get to our results, but not much. These are still really easy. So we need to untangle these a little bit. Part A. So let's start by solving for sine of theta. Okay, so think of it as one little unit, one little thing. We want to solve for it. So it's the same as solving 2x minus 1 equals to 0, where x equals sine of theta. Right? So we add 1, divide by 2. So either way, we end up with sine of theta equals to 1/2. And we've already dealt with this one. My God, that's getting really annoying. We've already dealt with this one. Sine of theta equals to 1/2. That's equal to 30 degrees. Right, so theta equals to sine inverse of 1/2. And so theta equals to 30 degrees. And we saw earlier that that must mean that also theta equals to 150 degrees. The sign is positive in quadrant 1 and quadrant 2. And then we can get to all the other answers by adding or subtracting multiples of 360 k plus or minus 360 degrees k. Good. Where k, again, is equal to 0, 1, 2, 3, ... Any questions about this one? Exactly like the previous one, I just didn't spend much time working on this because the only thing that's new is here that we needed to do a little bit of work to solve for sine of theta. Good. The second one, tangent, part B, we have tangent squared theta minus 3 equals to 0. Same thing, very little work needs to be done to solve this. We have tangent of theta squared equals to 3. So then we have tangent of theta equals to plus or minus root 3. Okay, so now when we think about our triangles, we have 60 degrees here, this is root 3, this is 1. Tangent is opposite over adjacent, so 60 degrees is one solution. Good, 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 good. And that takes care of, in quadrant 1, it's 60 degrees. But then in quadrant 2, there's going to be another one that works such that its reference angle is 60 degrees. So I'm going to need every single case that happens, well, in quadrant 1 and quadrant 4, let's do the quadrant 1 and quadrant 4. We have quadrant 1, of course, was that 60 degrees. But then in quadrant 4, well, that's just going to be minus 60 degrees. Good. Questions? This is 1, this is root 3, this is minus root 3. Right, and then that'll give me this minus 1. Good, and then if we think about our graph for tangent, right, remember our kind of sketching it again, it has a period of pi over 2, so this goes this way, and this goes this way, and then this goes this way. There's another one over there, right? So that's the tangent one. So we have the case where we have positive root 3 in quadrant 1 is going to lead you to 60 degrees. And the case where it gives us negative root 3 is over here. That leads me to negative 60 degrees. Good. And because it's periodic, all we have to do is add multiples of 180 degrees to both of them. So usually books don't like to present any answers with negatives if we can avoid it. So the first positive one that results, the first positive one that results from this angle here is to take this guy, and if you go over here, we get to this guy. This is plus 180. So that means that this is 120 degrees. Good. Good, good. Okay, so we like to present the first positive answer from that guy. So our final answer is going to be presented as theta equals to 60 degrees plus or minus 180 degrees K, right? And that's all the ones that come from here, because we can always add and subtract multiples of 360 and get all the angles such that sine of that angle equal positive root 3. And then we can present the other one as theta equals to 120 degrees the first positive answer. You could have also put minus 60 here, plus or minus 180 degrees K. Again, this is where K equals 0, 1, 2, 3, and so on and so forth, and so we have all our answers. Good. Questions, 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 questions? Right? We should, kind of come back and confirm that our results are going to work out, and they will, based on the way the equation is framed, right? Because if I can come up with all the angles such that tangent of that angle equals either positive or negative root 3, then squaring it is going to give me a positive 3, and 3 minus 3 is 0. Any questions? Questions, 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 questions? See what the author did. Similar things. Yep. Yep. Oh, they put it back in radians, so that's good. And plus or minus root 3. Yep. And then, because the tangent period pi for the first solution. Okay, so they left it as minus 60 degrees, but again, you can also move it forward. Good. Any questions? So this is my solution of 60 plus 180k, and this is negative 60 plus 180k, which is the same thing as positive 120 plus 180k in degrees. Good. Okay, trig equations involving factoring. So how about if we wanted to solve this one now? So we have cosine 2 cosine squared theta minus 7 cosine theta plus 3 equals to 0. So finally, they're getting a little more interesting. So consider a substitution. Let u equal to cosine of theta. So if we did a substitution, this would be 2u squared minus 7u plus 3 equals to 0. Good. So now this is something we can factor. It's got a 2 out in front, so really the best way to try and do this is by the guess and check method. So we got 2u blank blank u blank equals 0. Right? And the reason I'm doing this is because 2u times u gives you 2u squared. So I need something that multiplies to 3, but adds to negative 7 when you FOIL it. So you just kind of have to check different things. I could put a 1 here and a 3 there, for example, and make them both positive and see what happens there. But that's not going to work out to make them both positive because I need something in the middle that's minus. So let's try putting them both as minuses. And then just check, right? Just guess and check, not too many variations. So this would be 2x squared, that works, and we end up with minus 6. What the hell just happened? 2u squared. Man, this thing is just going nuts. Minus 6u minus u gives you minus 7u plus 3. Okay, so that works out. Just guessing and checking the few variations available. And so now from the product principle, we can say that this must mean that 2u minus 1 equals to 0 is one solution, or u minus 3 equals to 0 is the other solution. We can solve for u and say that that must mean that 2u equals 1, so u equals to 1/2. And so cosine of theta equals to 1/2 is one of the possible solutions. From over here, we get that u equals to 3, so cosine of u, cosine of u, not cosine of theta, cosine of theta equals to 3, and we know that there's no such thing, right? No solution from here. The output of a cosine function is bounded between negative 1 and 1. Okay. But this one looks familiar. cosine equals to, cosine of theta equals to 1/2, that's going to be 60 degrees. Cosine of 60 degrees equals to 1/2. Right? Or you can just if that doesn't come to mind right away, then you can say theta equals to cosine inverse of 1/2. Put that on the calculator, and you'll see that you get 60 degrees. Right, that just comes from our standard triangle. 60 degrees, 1, 2, 1/2√3. Good. And now we have to think about the other ones. Cosine is positive 1/2 in quadrant 1. But cosine is also positive in quadrant 4. So if I go back to my unit circle kind of thoughts on this, I'm going to have this over here like this, 60 degrees. But then over here, where this is negative 60 degrees, we have another case where that's going to be true. So we can call it negative 60 degrees, or negative 60 degrees, or going from there to there has got to be then 300 degrees. Good. So that's the other answer. Theta equals to 300 degrees is the other answer. Questions? No. Graphically, if you remember the standard period of a cosine function, it comes down, comes back up like that. So we're looking for something that gives you 1/2, an angle such that cosine of that angle equals to 1/2. Well, there's this one, and that's the one that's 60 degrees. And then if you go all the way across to the other side, you get to the other one, which is 300 degrees. And then we know it's periodic, so we have to add and subtract multiples of 360 degrees to get to the rest. So theta equals to 60 degrees plus or minus 360 degrees k. And the other solution is theta equals to 300 degrees plus or minus 360 degrees k. Good. Questions? Let's figure it out. Oh, this is where k equals to 0, 1, 2, 3, 4, ... Any natural? K equals any natural. So that's in degrees, and then let's figure it out in radians. So 60 degrees, if you multiply it by pi over 180, gets you to pi over 3. So that's this thing, and that's 2 pi, no problem. Now to get to 300, you can also take 300 and multiply it by pi over 180 and reduce. That'll give you your answer. Or the other way you can do it is by noting that we got 300 by doing 360 minus 60, right? In quadrant 4, the reference angle is going to be 60 degrees. And that's how we got to that. So this is equal to 2 pi minus pi over 3 in radians. Common denominator is going to be a 3 over 3. We get 6 pi minus pi over 3 gets you to 5 pi over 3. Okay, so from that, we can put it all together and say theta equals to pi over 3 plus 2 pi k, and theta equals to 5 pi over 3 plus 2 pi k. And this is where k is, and notice that I just put pluses this time, so now I'm letting k equal negative. So k equals to ... could be -3, -2, -1, 0, 1, 2, 3, ... otherwise known as any integer. K equals any integer. And that's how we would write it in radians. Any questions? No questions, no questions. No? No? Simple? Straightforward? No questions? Let's see what the author did. I think this is the last one in this section. Same thing. Factored it equals cosine of 3. Yep, same thing. 5 pi over 3. And we get the same answer. Pi over 3 and then 5 pi over 3 plus 2k pi. Good. Same answer I got. 5 pi over 3. Yep, same answer. So no questions? Okay, last one in this section. Let's just squeeze this one in. We have 5 sine theta cosine theta plus 4 cosine theta equals to 0. Solve for theta. Okay, it's going to be, well, I think the first thing that really just kind of pops to mind, I think, is to factor out a cosine of theta. Right? If we factor out a cosine of theta, we end up with cosine of theta times 5 sine theta plus 4 equals 0. Because of the product principle, that must mean that cosine of theta equals to 0 is one solution. And that must mean that 5 sine of theta plus 4 equals another solution. So sine of theta equals to negative 4/5. Or sine of theta equals to negative 0.8. We ran into this one before. This is not one of our standard values, so we're going to have to use our sine inverse function. Sine inverse of negative 0.80. So let's figure out what that is. Okay, so sine inverse of 0.8 is 5313 degrees. 5313 degrees. Theta equals to 53.13 degrees. And now we have to think about where is the other case. Where is this going to work out? So sine of, wait a minute, I think I didn't put negative. This is not right. It's got to give you negative 53.13 degrees, right? Yeah, it's supposed to be negative 0.8. Inverse, sine inverse of negative 0.80, close parentheses, negative 53.13 degrees. In fact, let's just leave that open. Okay, so back to here. Stop. So this is negative 53.13 degrees. So if we think about the sine function, it comes from there, comes up, comes down, comes that way, comes down, comes that way. And remember that the sine inverse function is only valid for this little segment of the sine function. So when we said, what is the value that gives you negative 0.8, negative 0.8, it said, oh, okay, that's this angle over here, negative 53.13. Okay, but there are there's another one. So if you get to, if you go over across this way, we get to this one, and then we get to this one. Right? And if you go this way, you get to this one. Okay, so if we add 360 degrees, 360 degrees, we get to this one. Good. And it's minus, so that's going to give us in quadrant 4. Okay, so man, this thing is just a battle. Why does it keep zooming? Did one of you guys just take control of my computer and you're messing with me? Is that what's happening here? This would be a great prank. Great, I'm giving you ideas. Plus 360. Okay, so plus 360, so that would be 350 theta equals 306.87 degrees. And that's clearly in quadrant 4. And that makes sense that sine is negative in quadrant 4. But also, sine is negative in quadrant 3. So if we think about our unit circle, let's see what we have so far. We have that if we are in quadrant 4 like this, and we have minus negative 53.13 degrees, or equivalently, if we go like this and go that way, we get to 306 degrees. Okay, we found this over here. This is the triangle that gives us the result we're looking for. But there's also another triangle over in quadrant 3 that's also going to work out. We go over here and we go over here. Sine is also negative in quadrant 3. And I need this to be a reference angle. This guy here needs to be a reference angle of 53.13, but in quadrant 3. So that lets me conclude that this, an angle starting from here but ending there, must be 180 degrees plus 53.13. 180 degrees plus 53.13, right? Which equals to 233.13. Any questions? No? 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 Okay, so that must mean that this angle right here, this one is the one that is 306.87 degrees, and this one must be the one that is 233.13 degrees. Good. And we can check them with our calculator to confirm that that is true. So let's confirm that all of these angles work out with our calculator. So it must be true that sine of negative 53.13 is approximately negative 0.8, with rounding issues in mind. Okay, and then we also figured out that if we add 360 degrees to that, it must be true that sine of positive 306.87 is going to give you the same result. Yep, same thing. And then we also figured out that if we go over to quadrant 2, we need to get to this guy over here, which is equal to 233.13. So sine of 233.13 also gives you the same output. Right? No matter how you slice it, you get negative 0.8. Okay, so we found the two angles in the standard period from 0 to 360 degrees. And now all we have to do to find the rest, or to write down the rest, is to add multiples of 360 to this. Okay, so our answer then is going to be theta equals to 306.87 degrees plus or minus 360K. And then the other one is theta equals to 233.13 plus or minus 360 degrees K. Right? But that's just half our answer, because that is all stemming from up here. Right? Let's go back to the original question. So we factored it, we separated it, and so we followed this part of it. 5 sine theta plus 4 equals to 0. That gave us sine of theta equals to negative 4/5. Sine of theta equals to negative 0.8. We found that our calculator is going to give us this answer. Right? Our calculator only gives us results in quadrants 1 and quadrant 4, from negative 90 to positive 90 degrees. Then we have to use our know-how to figure out that there's in fact this one in quadrant 4 and this one in quadrant 3. Okay, but now coming back to this guy, we have to find the other answers. This one should be easier if you think about the cosine function. The cosine function is going to have a standard graph that looks like this. Comes down, comes back up, comes back that way, and it goes through 0, right? Cosine of theta equals to 0. That's at pi over 2 and at 3 pi over 2. So that's what this is. Right? That's just a standard one. We don't need a calculator for that. Theta equals to cosine inverse of 0, which means that theta equals to pi over 2, or, which is the same thing as 90 degrees, or theta equals to 3 pi over 2, which leads to 270 degrees. Good. So we can put them all together and combined with these to give us our answers. Theta equals to 90 degrees, sticking to degrees, plus 360 K, plus or minus 360K. And the other one is theta equals to 270 degrees, plus or minus 360 degrees K. degrees K. This is where K equals 0, 1, 2, 3, or K equals any integers. And there's our solutions. Lots of different angles can result in a true statement for these. Right? So any one of those angles, if we come back and replace theta by any one of those angles, we should be able to get a true statement. We should also confirm that our answers are all true, or make sure that we don't have any phantom solutions. But that really becomes an issue when we take square roots of both sides, or square both sides. And we didn't have to do that here, so I think we should be fine. Good? Questions, questions, questions? Let's double check that's what the author did. Factored, we have cosine of 0, we have sine inverse of 0.8. So they left it in radians. So negative 0.93 in radians, quadrant 4, then pi plus 0.93 gets you to quadrant 3. This is a good graph. Let me zoom in on it. So instead of degrees, the author left it in radians. This is in quadrant 4. So here it is, negative 0.93. Good. So if you go all the way around, we end up with positive 0.93 plus pi to get to this one. Quadrants 3, quadrant 4. Once we find those two values, then all we have to do is add multiples of 2 pi in order to get to all our solutions. This is the cosine. Cosine of 0, cosine of theta equals to 0 is going to give us these two answers. And then leaving the others in radian form is going to give us these two. Any questions, any questions, any questions? This 4.04 is equal to pi plus 0.93, in case you're wondering where that came from. Questions, 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 questions? No? 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 Okay, this is a good place to stop then. We're almost done with chapter 7. There's only one more section. We'll finish it up tomorrow. It's more fun with trig equations, just slightly harder ones, but same concept. Nothing really new, I don't think. I wouldn't say that there's anything new in the next section. It's just more complicated trig equations that we get to play with. And then we'll be done with chapter 7. Okay? Any questions before we go then on anything? No? 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 Okay, I'll see you tomorrow then.
Awesome. Thank you.
You're welcome.